Hello, everyone. My name is Paul Lapis, and I'm a Principal Product Manager at AWS. I'm passionate about helping customers leverage their data to gain insights and make critical business decisions. At AWS, I focus on automation and the self-tuning capabilities of Amazon. Amazon Redshift enables users to scale up to meet user demand and optimize queries for performance for the most complex workloads. Today, we will cover how Amazon Redshift self-tuning features optimize cluster performance, and help you gain an understanding of how to dramatically reduce administrative overhead. We will also cover some real-world use cases and end with a brief demo of automatic table optimization. To start off, I'll share with you some of the reasons why customers have decided to choose Amazon Redshift. First is our lakehouse architecture. Redshift Spectrum has enabled customers to query the S3 data lake where it lives. As more customers want to query all their data, we've expanded the capabilities to query relational databases with federated queries to combine with your operational data. Second, Redshift provides fast performance at any scale. Whether you are just starting or an advanced customer, Redshift provides performance and scales to your needs. Our RA3 nodes have enabled best-in-class performance where they can now scale compute and storage independently. Aqua is built on RA3s and provides a new hardware-accelerated cache to boost your queries. Finally, we have helped customers get the best value and bang for the buck. Most importantly, we make your costs predictable even as your workload scales. Before we dive in, I wanted to share what we hear from customers are the key trends driving demand for automation. First, there is more and more data. As we all know, the amount of data that is generated has exploded over the past 20 years. The proliferation of IoT devices and smartphones have accelerated the amount of data that is generated every day. But more importantly, the majority of this data is now generated on the cloud. This is because customers can achieve instant durability and scalability in the cloud without worrying about the underlying infrastructure. Due to this trend, over the past decade, customer data problems have increased from terabytes to petabytes, and now we see customers with even exabytes of data. At the same time, the number of users within an organization that want access to data is growing. Fast queries are an important aspect because it means that users can deliver insights more quickly, data can be more up to date, and data scientists can iterate more quickly on their projects. And the rise of data products has shifted team activities away from basic reporting and business intelligence functions, although those are still very important, to being part of data operations, embedded in product teams, and behaving as partners in their product development process. All of this leads to specialization of roles, as data teams want to focus more time and energy into getting value out of data versus traditional DBA tasks like cluster management, performance management, and infrastructure. This has led to an increased focus on two primary roles. The first are data analysts and data scientists, who work with business users to understand data requirements, drill down into data for deep insights, develop models, and perform exploratory data analysis. Then, data and analytics engineers, they provide the semantic layer, clean data for analytics by downstream users. They deploy ELT, data pipelines, build tests, maintain data documentation and definitions, and they train users on how to use those data platforms. All of this leads to demand for data warehousing infrastructure that is easier to use, so teams can invest more energy on higher value activities. Let's take a closer look into Amazon Redshift's self-tuning capabilities. Amazon Redshift continuously monitors user workloads and uses sophisticated algorithms to find ways to improve the physical layout of data to optimize query speeds and tune queries. By using automation to tune the cluster, customers can decrease administrative costs for Amazon Redshift while getting the best possible performance. Amazon Redshift invests in self-tuning capabilities across 5 areas. The first is workload management, where we ensure that your most important workloads can meet SLAs and you can protect your data warehouse from rogue and wasteful queries consuming unnecessary resources. We invest in advanced monitoring to continuously detect and remediate issues that may affect cluster performance. On the infrastructure side, Redshift tuning will automatically add physical resources, nodes to meet demand, as well as handle software upgrades and patching. And for individual queries, we will tune them to improve query speed automatically by optimizing query planners and leveraging materialized views automatically. And finally is table design, where we automatically select the correct way that data is physically laid out to make sure that the queries running against it are as fast as possible. Let's take a look at the features more closely. Over the past few years, Amazon Redshift has invested in automation for common maintenance tasks like vacuum, analyze, table sort, and advisors for sort keys and distribution keys. Automated vacuum means that storage space is reclaimed automatically. Analyze means that the Redshift query planner can work more efficiently. And sorting data ensures that queries can find data much more quickly. Automatic table optimization selects the best sort keys and disk keys to optimize performance for the cluster's workload. If Amazon Redshift determines that applying a key will improve performance, tables will be automatically altered without requiring any administrator intervention. In order to get even more value out of Redshift, we have improved the workload manager by leveraging machine learning to get more query throughput for your high priority workloads. This means that you can run more queries without adding additional nodes or cost to your cluster. And we're always looking for ways to tune queries to get maximum speed. Earlier this year, we launched Materialized views, and we are announcing automatic refresh and rewrite of Materialized views. This means that queries which can benefit from existing views will be automatically rewritten in order to take advantage of those without the user having to make any changes to the SQL. Let's take a closer look at the workload manager. To get an understanding of why workload management is important, consider how Amazon Redshift customers run a very complex mix of workloads, all competing at once for the same resources. For example, frequent data loading competes with business-critical dashboard queries, or high-volume transformation jobs compete with data science exploration work. Each type of workload has different resource needs and query latency requirements and SLA expectations. So how do you manage these expectations while optimizing cost and performance for your data warehouse? A successful workload management scheme effectively manages resources, ensures highly efficient resource utilization, and maximizes return on investment. One approach to solve this problem is to simply add more resources. This approach, though, is problematic because it leads to unpredictable spending and high invoices. The Redshift WLM brings order to this environment. It helps users maximize throughput and get consistent query performance for the most demanding workloads. It stabilizes response times of important work, prioritizes users, and protects users from poorly written queries, and manages system resources based on user-defined query priorities. These are accomplished with features like query priorities. You can now ensure that high-priority workloads can get preferential treatment in Redshift, including more resources during busy times, and query monitoring rules. These QMR provides ways to manage unexpected situations like detecting and preventing runaway or expensive queries from consuming system resources. We are excited to announce significant improvements to the workload manager. It now includes dynamic concurrency, which controls the number of, determines the number of slots to maintain the system usage optimally and deliver maximum throughput. It also now uses machine learning to predict the amount of resources a query will need and create a slot on the fly and provide only that much memory which is estimated that is needed by that query. And the benefit of this is that we can pack even more queries into the system. We've also enhanced the short query acceleration feature. In addition to detecting short queries, SQA now automatically is activated. We have a mode called Turbo Boost mode that when it detects queue buildup and waiting queries that don't require a lot of resources, it will allow them to be executed to allow for more consistent query performance for all queries regardless of a priority, as well as more efficient resources overall. If you manually manage your workloads today, we recommend that you switch over to automatic WLM. Start by creating a new parameter group for automatic WLM. You can also enable concurrency scaling for any query queue to automatically scale up your cluster to handle virtually an unlimited number of concurrent queries with consistently fast performance. Next, let's talk about how Amazon Redshift automatically tunes queries. Materialized views provide significantly faster query performance for repeated and predictable analytical workloads, such as dashboarding, queries from business intelligence, BI tools, and ELT data processing. Using materialized views, you can store the pre-computed results of queries and efficiently maintain them by incrementally processing the latest changes whenever the source data changes. MVs can be manually refreshed, or you can schedule the refresh. Amazon Redshift now provides a new option to automatically refresh materialized views, which simplifies the usage of up-to-date materialized views to accelerate query performance. As you submit a query, the automatic query rewrite capability leverages one or more relevant materialized views and can improve query performance by orders of magnitude using existing views. They can be leveraged even in cases when the specific view may not be explicitly referenced in the queries. Now let's take a closer look at automatic table optimization. This is a new self-tuning capability that optimizes the physical design of tables by automatically setting sort keys and distribution keys. Distribution and sort keys are table properties that define how data is physically stored. While Amazon Redshift has industry-leading performance without setting sort or distribution keys, applying keys can result in significant performance benefits for the most demanding workloads. Previously, customers had to apply sort and distribution keys manually, automatic table optimization continuously observes how queries interact with tables and uses machine learning to select the best sort and keys for the cluster's workload. By default, tables created without explicitly defining sort keys or distribution keys are set to auto. At the time of table creation, you can also explicitly set a sort or distribution key manually. If you set the sort or distribution key, then the table is not automatically managed. To enable an existing table to be automatically optimized, use the alter statement options to change the table style to auto. You might also choose to define automation for sort keys, but not for distribution keys, and vice versa. You can remove a table from automatic optimization as well. This involves selecting an explicit sort key or distribution key. To change distribution style, just specify a distribution style using the alter command. And for sort, you can either pick a key or change the sort key to none. You can also monitor the actions taken by automation via system tables. We have added a view which records the optimizations which are going to be applied in the future, as well as a table that shows an audit log of all the actions taken by Amazon Redshift, and also the previous state of the table. Optimizations made by the automatic table optimization feature have been shown to increase cluster performance by up to 34% using the TPC-DS benchmark versus a cluster without automatic table optimization. Next, I'll explain how Amazon Redshift manages how table data is distributed automatically. When tables are first created, they are initially set to even or all distribution based on table size. Tables with a small number of rows are set to all distribution because this style optimizes for performance. Then, as the table grows in size, Redshift will automatically change the style to even. Now, the main benefit of distribution keys is to optimize joins. A query that joins multiple tables will run much faster if those tables can be joined on their distribution key columns because it minimizes the amount of broadcast traffic on the network. Amazon Redshift determines the appropriate key by constructing a graph representation of the SQL join history and optimizing for data transferred across nodes when joins occur. When Redshift has enough confidence that adding a key will improve query performance, automatic table optimization will execute an alter table command to modify the distribution key. Now, because redistribution for a large table may take a long time, Redshift performs this operation in the background in an entirely separate location of the cluster in a temporary table. Now, in order to minimize impact to user queries, the redistribution operation will pause itself if the cluster gets busy and then resume exactly where it left off. And because the process is occurring on a separate area of the cluster, existing queries are not interrupted during this process. Then, only at the end of the process, when the redistribution is finished and the table is ready to be cut over, a temporary lock is obtained on the table, at which point queries may see a few seconds of queuing. Now, let's examine how sort style automation works. Choosing the most appropriate sort key for a table accelerates the performance of queries, especially those with range-restricted predicates like where and order by clauses, by requiring less data to be read from disk. When tables are first created, tables do not have a sort key. Automatic table optimization determines the best sort key for a table by analyzing the cluster workload to determine which columns are used frequently in range-restricted scans. And if the system determines that a sort key will improve speed, it will execute an alter table, alter sort command to apply a key to that table. Now, the actual act of sorting a table is done by the existing automatic table sort feature. This feature provides an efficient and automated way to maintain sort order of the data in Redshift to continuously optimize query performance. With automatic table sort, Redshift runs the sorting in the background and reorganizes the data in tables to maintain sort order and provide optimal performance. Now, this operation does not interrupt query processing, and it reduces the compute resources required by operating only on frequently accessed blocks of data. It uses machine learning to prioritize which blocks of the table to sort by analyzing historical query patterns. Automatic table sort is really useful in cases with continuous ingestion of data and ETL batch processing operations such as incremental daily updates. Redshift will provide a recommendation if there is a benefit to explicitly running vacuum sort on a given table. Now, the next feature I wanted to discuss is the Amazon Redshift Advisor. Since launching in 2018, the Redshift Advisor has helped thousands of customers tune Amazon Redshift by providing actionable advice to save on cost and optimize performance. The Advisor technology is the basis for many of Amazon Redshift's automation features. It is continuously monitoring your workload and metadata of your data and applying ML techniques to surface recommendations. Now, customers have asked us just to simply automate the recommendations made by the advisor, and this is what we have done with features like automatic table optimization, automatic table sort, automatic vacuum analyze, and the automatic workload manager. But still, even though Redshift has built automation to automatically apply many of the advisor recommendations, there are still some expert users who still value the control they get from tuning their cluster manually. And Redshift continues to allow them to do that by opting out of automation. For example, a customer may choose to use the manual workload manager and configure memory and concurrency settings manually, or opt out of automatic table optimization by defining keys and sort keys and disk keys for their tables themselves, or they can just run vacuum and analyze commands manually and turn off those automations as well. Let's take a closer look at the advisor recommendations. If you frequently run copy to ingest data, the Redshift Advisor may recommend compression or reorganization of files in S3 to take advantage of the parallelism of the Redshift architecture. The advisor also helps save money by identifying clusters in your account which are idle. If the advisor detects that no user queries have run on a cluster for 7 days, it will recommend for you to pause or shut down the cluster. Also, it will find opportunities to compress table data to save on storage costs. Some of our customers elect to manually configure their workload manager because they have highly customized environments. For these customers, the advisor may detect ways to optimize the memory and slot setting for WLM in order to save resources and get more throughput. For the vast majority of customers, we recommend just to use the automatic version of the workload manager, which is the default. Finally, the advisor will surface sort and disk key recommendations for tables or for tables that require vacuum or analyze to be run. Now, this is useful for tables that are not under management of automatic table optimization. And the advisor recommendations are visible by clicking on the Advisor tab in the Amazon Redshift console. Now, let's take a look at how these self-tuning features of Amazon Redshift apply to real-world use cases. This is a common reference architecture for how Amazon Redshift can be used for ETL processing and BI use cases. In this model, data is ingested into a staging schema, and there are three worker personas. There's ingest, ETL, and then the users that run queries. In terms of read and write access, the general rule of thumb is that users in each role should only have access to the schemas and tables that they need and no more. So the ingest workers have write and read access to the staging schema. The ETL jobs can read the staging data and write to the prepared schema. And then users only have read-only access to prepared data. So how can self-tuning features optimize performance in use cases with continuous ingestion of data and ETL batch processing operations such as incremental daily updates? Well, first, on our staging data, if the tables are configured with auto, then automatic table optimization will detect the correct sort keys and disk keys and apply those automatically for super fast ETL processing. Next, we can set query priorities in the workload manager for the ETL user. In our example, we would prefer for the ETL job for the users to have the highest priority and for the ETL jobs to have medium priority. So that's how we configure query priorities in the workload manager. And then finally, the automatic table sort and vacuum operations will maintain the sort order of those tables and make sure that we're reclaiming space when we're deleting rows on ingestion. On the right side of that reference architecture, let's take a look at the BI and the user use cases. First, we will set the sort and distall to auto as well, just as before. This is even more important in this scenario because users, the administrators of Redshift, really can't easily predict the queries that the end users are going to run. And so setting auto for those tables will pick the right keys automatically based on the actual end user queries. And as we said before, in this example, we do want our end users to have the highest priority and to provide the best SLA for them. So we will set query priorities to high for the users. We also have some novice users to provide some guardrails to ensure that rogue or expensive queries don't consume resources unnecessarily. And to do this, we will configure some QMR rules to automatically abort queries that return too many rows or to automatically abort queries that perform nested loop joins. Finally, we will create some materialized views for known common aggregations, and then we will expect that the automatic query features of Amazon Redshift will automatically take materialized views to speed up queries. Now I'd like to take a deep dive and share a demo of automatic table optimization. This demo will show how automatic table optimization will pick encoding, sort keys, and disk keys for tables based on workload without requiring any user intervention, and will quantify the improvements in query speeds. We'll be working with two tables in this demo. One is called part, the other is called line item. Here's the DDL that we ran. As you can see, there's no sort key or disk style properties included in the create table statement. That means to Redshift that the tables will be defined as auto and that you want Redshift to manage the sort keys and disk style for those tables. You can still, specify sort keys and disk keys as part of the create table statement. If you do so, then the table will not be automatically managed by Redshift. One of the great features of Redshift is automatically selecting compression encodings based on table data. The picking and encoding for a column will reduce storage footprint as well as increase query speeds. The copy statement will take a sample of the data in S3. It'll look at the first 100,000 rows and then based on that, we'll select the optimal encoding algorithm. In this case, it selected a combination of sort keys and disk keys of these tables before we execute any queries on them. Querying the SVB table info table will show the current status, and both tables are set to auto for disk style and sort key. The disk style is set to even. This is picked automatically by Redshift based on table size. If the table had been a small table, then Redshift would have selected an all distribution style. That's because that's optimal for query speeds. And then as the table would grow in size, it would convert it back to even. We will be executing two queries. The first one is a join with a where clause. We will be joining both tables on the part key column as well as filtering by ship date. And then the second query is a select of the line item table, also filtering by ship date. What we should expect to see is, because we're joining on the part key column on both of these tables, that this is the optimal distribution key. Picking a distribution key in Redshift will collocate data for those columns with the same values on the same nodes, so that when a join happens, data doesn't have to be shuffled around the nodes in order to materialize the query result. And for sorting, once a sort key is applied, then Redshift has a feature called automatic table sort that will, in the background, constantly keep tables sorted, so that when where clauses or order bys are done on the table, the query engine knows exactly where to go to return the results without having to scan the entire table. So over some time, what you should expect is to run a query a couple dozen times before an optimization is surfaced, and that's because the algorithms need enough data to make a determination of the optimal settings to improve performance. And what you should expect to see is, after after a few hours after you start running queries, that you should see entries. You will see in the Amazon Redshift Advisor in the console. They are now shown in the system table. As well as each of the DDL statements, we are also bringing forth the setting of the tables, whether or not they're set to auto. If the table is set to auto, there's a true in this, a T in the auto eligible column, which means that Redshift will automatically apply this DDL for you. And if not, then it's set to false, in which case we'll rely on the user to execute the alter table statement if you choose to. The actions table will show a real-time log of what ATO is doing, and when an optimization starts being worked on, it'll drop a log, as well as when it completes, it'll show the completion status as well as what the previous setting was, and in this way you can keep track of the changes that ATO is making on the system. Okay, so some time has passed. Let's look at the keys that ATO picked. So as expected, on the line item table, this was the table that we were both joining on, as well as doing a select statement on a where clause. ATO selected a distribution key of part key, as well as a sort key of ship date. And then for the part table, ATO picked also the same distribution key of part key and no sort key. And that's because we did not run any queries that were doing any orders or filters or whereby clauses on the part table. And so this is what we expected to see. Now let's quantify the performance improvement of sort keys and disk keys on these tables. When we ran these queries, a query table that keeps a log of start time and end time of queries in order to measure the before and after improvements. For the first query, the one with the join, the Runtime went from 312 milliseconds to 284 milliseconds, which represents an almost 9% improvement in performance. We saw much greater performance on the second query by adding a sort key. That one improved from 487 to 318, which represents a 35% increase in performance without having to do anything. Thank you. This was a demo of how automatic table optimization improves query speeds by automatically setting sort keys, disk keys, and column encoding. Thank you for joining this session today. Here are a few things to check out to keep learning more about Amazon Redshift, the Lakehouse approach to data warehousing. For next steps, if you're already using Redshift, I encourage you to check in with your account team to continue to learn. Ensure you are taking advantage of the latest features. Check with your account team for a free optimization session. If you are just getting started with Amazon Redshift, I encourage you to ask your account team for a 10-minute demo and to visit the playbook in our documentation to learn more about starting a proof of concept. Of course, we're here to help with that too. And if you aren't sure who to reach out to, you can request help from AWS with a link on the screen.